our plan is to just go over the evidence of the Big Bang Theory and fill in the note that we got just before the break. Now, at this point, we've already watched our video in class on what the Big Bang Theory is and the main steps of it. And so we have a general idea of what it is. Now, all we're after is looking at some of the evidence that allows us to come with it. Now, remember, our Big Bang Theory tells us how our universe formed, how it went from an extremely hot, dense state, a singularity, into the universe we have. And it looks at the period of really rapid expansion at the beginning where we had no universe to the universe we have now, and how our rate of expansion is increasing. Okay? And during the expansion, the universe cooled, which allowed us to then form all of the matter that we have, and ultimately all of the galaxies and everything else. Okay? Based on our best estimates, and we'll talk about where this number comes from, our universe is approximately 13.8 billion years old. Okay? But this is not the diameter of the universe that we can see. We can actually see a diameter of the universe of approximately 92 light years. And this is because we can see in both directions, and then also the expansion of the universe has caused it to go outwards and increase in size. So we can actually see approximately 46 light years in any direction. Okay, we know that after our initial rapid expansion of space expanding into itself, we had our various subatomic particles form. Initially, we had our protons form, and then after a little while, we had our neutrons, and then a lot of the neutrons were converted back into protons. And then a little while later, it cooled enough for electrons and for the protons to gather the electrons, so that we had now neutral atoms. And after we had our neutral atoms, that then allowed for nebulas and galaxies to form. And our very first early stars, because the universe hadn't expanded so much, were very dense and formed in very dense nebulas. And so as a result, this allowed for very massive stars early on that burned through their fuel quickly and went through supernovas. And these supernovas produced the heavier elements. Now, these supernovas that are occurring in dense, large nebulas are still occurring today, and are still producing more of the heavy elements that we have in our universe. Okay, so this is a classic image that is used to demonstrate what we know about the Big Bang and the different things that we have. Okay, and so we have our Big Bang occur. We go from our singularity to the universe. We have a period of rapid expansion, our inflation period, at which point then it starts to cool, and we start to get the formation of our protons. Okay, and then we have it expand more and more, cooling and everything. And then we have the formation of our first atoms. And then after about 1 million years, we start to get the formation of galaxies and stars. And then we still have more expansion occurring, and it's expanding at an accelerated rate. And then we have the formation of our solar system about 9 billion years or so. And then we have life on Earth starting to form. Okay? And then at some point in the future, it'll continue to go on. And there are a number of theories as to what will ultimately happen to the universe. Now, there are 4 main pillars of evidence for the Big Bang Theory. There is lots of evidence, other evidence as well, but there are 4 main pieces that all astronomers agree upon. And this evidence, the strength of it is why it's called a capital T theory. Okay? One is large-scale homogeneity of the universe, and we'll talk about what this means. The redshift and the work from Hubble. the fact that we have lots of light elements and our cosmic background radiation. Okay, then we have some other evidence, our age of our stars. One of our first pieces of evidence for our Big Bang Theory is the homogeneity of the universe. When we look within galaxies, they have unique features and different structures. So what I mean by that is they have different stars, they have different abundances of big stars and little stars, they have different planets, but when we look at the large scale, they have similar features. They have stars made out of the same materials, they have stars that go through the same life process, they have the same abundance of elements roughly between galaxies. Depending on the number of stars that have gone supernova within a galaxy, one may have more or less heavier elements, but the fact that it's mainly matter, there's no antimatter, it's energy, the abundance of dark matter, dark energy, it's the same. So because we have the similarity in structure on a large scale, this is one of our pieces of evidence. Okay, and so this would be the note that you had. Okay, on a large scale, the universe is roughly the same. On the small scale, they're different. When we look at the scale of hundreds of millions of light years, we have generally the same structure of the universe.